Greetings and welcome to the video for problem set number 3 of Chemistry 223. And in this chapter, chapter 14, we're going to look over acids and bases and see the kind of things that chemists can do to predict how they're going to react and stuff like that. So like the other problem sets that we've done so far, I encourage you to have a periodic table next to you. I recommend the mhchem.org/per-tab periodic table because that's the one we'll use throughout the term. I encourage you also to try the problems on your own first, and then you can use this video to kind of self-correct. When you're going through the video, you're welcome to scrub through it. You don't have to watch it from start to finish unless you'd like to, of course, which is fantastic. And most importantly, make sure that you mark every problem on your problem set. Mark the ones that are correct with some kind of self-correct symbol, and there's a couple of different varieties that people have used there on the right-hand side. Also make sure that you correct the ones that are wrong, and it's totally fine to make a incorrect assumption on a problem. Just self-correct your work, show how you do it better next time, and you'll learn and be good to go for quizzes and exams, stuff like that. If you have questions on any of this material, reach out to me. You can also reach out to the AVID/LSC Center. Their website is mhcc.edu/avid. They have free chemistry tutoring for you. I recommend it. They're pretty cool people up there, and I think you'll like them. So it's not too bad. Should be pretty similar to the other problem sets you've done so far. You will need one table for this problem set. It's the table of acids and bases for Chem 223 table. It is found in problem set number 3. You can also find it there at mhchem.org/capital K little a, capital K little b. And you will need those values there to complete this problem set. And make sure that you use these values of Ka and Kb to complete your problems in this whole term, because these are the ones that we'll use. You'll find other values for some of these acids and bases online, and that's totally fine. But to make sense of the problems we're going to do, it does help to use these specific values. So let me know if you have any questions. Without further ado, let's get into the problem set. Question number 1, it says we've got these reactions, and it wants to know the Bronsted acid and the Bronsted base, as well, as the conjugate partner. So it wants to know the conjugate acid and the conjugate base, and no problem. So a Bronsted acid and a Bronsted base, that's the main acid-base theory we're going to use. And a Bronsted acid is a hydrogen H+ donator, and the Bronsted base is something that can accept the H+. All right, it's a Bronsted acid acceptor. And on a reaction like this, to figure out what's going on here, you want to look for the species which are similar. So on A, notice that this thing right here, HCO2H, looks a heck of a lot like HCO2-. Now, on the right-hand side, you're missing the H+. That's why there's a -1 there. On the left-hand side, you've got the H+, but so it takes care of the -1. Those two are what they call conjugates. Conjugate is nothing more than two species related by an H+, and the part with more H+ is the acid, and the part with less H+ is the base. So the HCO2H is going to be the acid. It's a Bronsted acid. It's donating an H+, and in the process it makes the conjugate base, all right, HCO2-. It's missing that H+, so it's no longer there. Now, if this is the acid, HCO2H, then water here, believe it or not, is actually acting like a base. It's going to accept this H+ from the acid, and it's going to make hydronium, H3O+. So notice here that the HCO2H, that Bronsted acid, it's reacting with a Bronsted base, something that can take the H+, which in this case is water. And on the other side, you've got HCO2-, the conjugate base of HCO2H, and you probably figured it out, hydronium, H3O+, that's the conjugate acid of water. So for this one, notice here how the acids and the bases and stuff, you've got an acid on the left and a base on the right, and an acid on the right and a base on the left. So for this first one, H2COH is the Bronsted acid. it's donating its H plus to H2O, the Bronsted base. HCO2H without the H plus is HCO2 minus, all right? And the the conjugate Bronsted acid of water then would be hydronium. So HCO2H and HCO2 minus, those are conjugates. Just like water and hydronium, those two are conjugates. They're related by an H plus. And again, if you ever get confused what's an acid or a base, remember acids have the more H plus and bases have less. So hydronium, more H plus, water has left, etc., etc. And you can go through all of these and do the same kind of thing. So the next one, H2S, has more H plus than HS minus, so it's the acid. The base, NH3, accepts the H plus from H2S to make NH4 plus, ammonium, so no big deal. And again, H2S and H minus, HS minus are conjugates, just like ammonia and ammonium are conjugates. The next one is kind of interesting. HSO4 minus has more H plus than sulfate, so those two are conjugates. HSO4 minus is the acid and sulfate is the conjugate base. Hydroxide here is the base. It's taking the H plus to make water. So here hydroxide is the Bronsted base, water is the conjugate acids. It's pretty cool. So all these acid-base reactions have an acid and base on the left and an acid and base on the right. The conjugates are related by H pluses, so the HCO2H and HCO2 minus we talked about, and the first one as well as water and hydronium. And finally, if you ever forget, acids always, in the Bronsted theory, have more H plus than the bases. So if you didn't know if OH minus in water, which one was which, well, water has more H plus, it's going to be the acid. And OH minus with less H plus is going to be the base. In this problem, we're going to continue on a little bit from what we did last time, and I'd like you to predict what the products will be of each of these acid-base reactions. And I want you to indicate what the acid and its conjugate base is, and the base and its conjugate acid, and all that kind of stuff. And so like before, something will transfer an H plus, that'll be the acid, to something else, which will be the base, and then the result then will have conjugates. And like before, you can usually tell which species is the acid. It'll have more H than the other one. I'll show you examples as we go through this one. So for the first one, we have perchloric acid, HClO4, which is one of the strong acids, and it's reacting with water. Now, all of the strong acids will act as acids, and they'll donate an H+, and whatever else is around it will essentially accept the H+. So in this case, then, the perchloric acid, acid A, as it's listed right there, is going to transfer an H+ to the base, which is water, base B. And in the process, then, you'll end up with H2O plus H+, which is H3O plus hydronium. Hydronium is the conjugate acid of B. And you also have then perchlorate, which is a polyatomic ion left over. That's the conjugate base of A. Now remember, if you don't know which is the acid and which is the base, compare them, all right? So for example, those two right there, HClO4 and ClO4 minus, are related by H+. You take away an H+ for perchloric acid, you've got perchlorate, add an H+ to perchlorate, and you have perchloric acid. So those are conjugates. And the one with more hydrogen is the acid. So perchloric acid obviously has an extra H+ that perchlorate does not. That's why it's the acid. And the same thing with water and hydronium. Hydronium has one more H+ than water. It's going to be the acid, and water will be the base, etc., etc. Now in the next one on B, you've got ammonium, NH4+, reacting with water. Now, if you remember from nitrogen's Lewis structures, nitrogen can only handle 4 bonds. It can't go more than 4. So tetrahedral is the maximum electron pair geometry that nitrogen can handle. NH4+ is going to donate an H+ to water, and it's going to make ammonia in the process, as well as then hydronium as well. NH4+ is the acid, and NH3 is the conjugate base. And again, you can see there's that relationship there, H plus. NH4 plus has more H plus, so it's the acid. NH3 has less H plus, so it's the base, etc., etc. Likewise, water will be the base in this problem, and hydronium will be the conjugate acid. Now, in these problems so far, water has always been the base, and that's just the way that these problems work out. But in reality, water can be both an acid and a base, especially when you have a substance like on C, the hydrogen phosphate ion. Hydrogen phosphate is one of a series of phosphate ions with hydrogens. You can have phosphate by itself, you can have two hydrogens with phosphate, all kinds of different things. So on the next one, I want you to show how hydrogen phosphate can be both an acid and a base, just like water can be an acid and a base. So the first one, let's think about hydrogen phosphate as an acid. So the hydrogen's going to donate from hydrogen phosphate to the water. It's going to make phosphate, the conjugate base of hydrogen phosphate, and hydronium will be created, the conjugate acid. And that's basically like the last two examples we've seen. Hydronium was created as water was the base on the reactant side. But really, there's no reason here why hydrogen phosphate has to be an acid. It could also be a base. So let's now think about water as an acid. So water can donate an H plus to hydrogen phosphate to make dihydrogen phosphate, H2PO4 minus. And in the process, then, you end up having hydroxide being created. So now if you look at these, water and hydroxide, they are related by an H plus. Water has donated an H plus, so it becomes hydroxide, the conjugate base, and hydroxide, if it gains an H plus, becomes water, the acid. And you can do the same thing for hydrogen phosphate on these. So you can see, like in the first one, hydrogen phosphate and phosphate, it donated an H plus to become phosphate, but on the second one, it accepted an H plus to become the dihydrogen phosphate. So this relationship then of H plus is important to distinguish what an acid and a base is. And also you can see that a lot of species, water being the most common by far, but a lot of these species, including hydrogen phosphate, can be both an acid and a base. So keep that in the back of your mind while we go through these problems. Here's three acid systems, each with their Kas. An Ka, an equilibrium constant based on an acid, you always write it as the acid plus water, and the products will be the conjugate base, which in this case is fluoride, and hydronium. So notice that A, acid, means hydronium is going to be formed, and we'll figure out that from going on. Now, these other acids, here's hydrogen phosphate again. This one here is acetic acid. And it says which one of these is the strongest acid. Now, an equilibrium constant K, as it gets closer to 1 or numbers greater than 1, that means you're going to have more product. And numbers K that are less than 1 mean more and more reactant favored. Now, strongest acid means more hydronium, all right? So the strongest acid is going to have the most hydronium, and you're going to have the most hydronium from the largest K. So in this problem, the largest K is HF. HF has the largest K. That means it's going to be the strongest acid. And conversely then, the weakest acid is going to have the smallest Ka, because that means less hydronium. So hydrogen phosphate is the smallest of the K. That's going to be the smallest. So in this problem, we would say that HF is the strongest acid because it has the largest Ka, and HPO4 minus 2 would be the weakest acid because it has the smallest Ka. Now, the conjugate base of HF, we already talked about, is fluoride. All right, fluoride is the conjugate base. And I put this in here because in Oregon, especially, once in a while they talk about fluorinating, adding fluoride to water. And from a dental perspective, it's really good, and some people are against it. And I don't care which way you want to fall on that argument. But I do want you to be aware that adding fluoride is actually quite different than adding chloride, bromide, or iodide. Fluoride is a weak base. And weak bases will affect your pH, which affects the nature and all the fish running around and all these kind of things. Again, I don't care which way you feel about it, but fluoride is quite different than the other halogens like chloride, bromide, and iodide. in that it does have basic properties. And that could be good or it could be bad, but I just want you to be aware of it. Now, the next two are kind of similar. The acid with the weakest conjugate base and the acid with the strongest conjugate base. Now, we said that Ka was the strongest acid. So if HF is the strongest acid. So if it's the strongest acid, then that must mean that the conjugate base fluoride is the weakest. Strong always goes to weak. So in this case then, the weakest conjugate base is going to come from the strongest acid. So fluoride is going to be the weakest of the bases there because it comes from the strongest acid. And likewise, if the weakest acid was HPO4 minus 2, that must mean that of the bases list there, phosphate would be the strongest of the bases, i.e. the phosphate would have the strongest kick to it, or hydrogen phosphate would be has the strongest conjugate base. So you can use the Kas as relative guides as to which one is strongest and weakest, and that can be kind of empowering. In this question, we're going to look at both pH and pKa expressions. So in the first question, we have a pKa of 8.95, and it says, what's its Ka value? Well, if we had a pH of 8.95 and we wanted the hydronium, we would go 10 to the power of minus pH to find hydronium. And we're going to do the same thing here with Ka. If you go 10 to the minus pKa or 10 to the minus 8.95, that gets you in your calculator 1.1 times 10 to the minus 9. That's the Ka value for this pKa value, which is kind of cool. So if you want to go from pKa to Ka, 10 to the minus pKa gives you Ka. And if you go minus log of Ka, you'll get pKa. And a quick note on sig figs here, you can see how the 8.95, there are 2 digits past the decimal, and that's why there are 2 sig figs. When you take a logarithm of a number, the number of sig figs is the number of digits past the decimal. So that's why it feels kind of like you're going from a 3 sig fig to a 2 sig fig, 8.95 to 1.1 times 10 to the minus 9. But when the logarithms and anti-logs, that's how it works out. So just FYI. The next one, we've got a weak base with a Kb, 1.5, 10 to the minus 9. What's the value of Ka for the conjugate acid? Okay, so just like we saw with acids and bases, Kw equals hydronium times hydroxide. Kw also equals Ka times Kb if they are conjugates of each other. So if the base and the acid are both weak and they're conjugates of each other, Ka times Kb equals Kw. So on B, to solve for Ka, we're going to take Kw, which is 1.0 times 10 to the minus 14th. We're going to divide it by Kb, 1.5 times 10 to the minus 9, to get Ka. And if you do that, it comes out to be 6.7 times 10 to the minus 6. So Kw equals Ka times Kb, assuming that they are conjugates. Just like Kw also equals hydronium times hydroxide. It's kind of a cool thing. It shows the power of that Kw value. Make sure that you know this. This is important. Now, the next problems are all about finding pH of either a strong or weak acid or a strong or weak base. So let's go through these and just remember how this all works. So HCl is a strong acid. It has a concentration of 0.30 moles per liter. What is the pH? If you have a strong acid, pH equals minus log of the concentration, which is minus log of 0.30. You want to use base 10 log, stuff like that, but it's pretty chill. So for strong acids, pH minus log the concentration of the acid, or minus log 0.30, and that comes out to be 0.52. The important part, strong acid pH equals minus log the concentration of the acid. So that would apply to HCl, HBr, HI, HNO3, and HClO4. pretty fine. Now the next one is a strong base, has a concentration 0.010. What's the pH of that? Strong bases, pH equals 14 plus log concentration strong base. So in your calculator, 14 plus log the concentration of the strong base, or 14 plus log 0.010, comes out to be 12.00, exactly, as a matter of fact. So strong base is 14 plus log concentration strong base, while strong acids, pH equals minus log concentration strong acid. Now when it comes to the weak acids and weak bases, the equilibrium constant, Ka for acids and Kb for bases, will become important. In a nutshell, when all is said and done, if 100 times K is less than C, and I'll just guarantee it will be from here on in, but if 100 times K is less than C, then hydronium equals square root Ka times Ca. And if you extend it out from there to pH, for example, pH will be minus log square root Ka times Ca. If you have a weak acid and you want to know the pH of it, you need Ka and Ca. You would take minus log square root Ka times Ca. So in your calculator, and you should try this to make sure you get this value, you want to go minus base 10 log square root parentheses 1.8 times 10 to the minus 5 times 0.10 other parentheses. And if you get 2.87, you are good to go. But notice again how the weak acids have a Ka dependence while the strong acids did not. Strong acids, you don't need to worry about Ks because it's 100% dissociated. But when it comes to weak acids, you must take into account that acid dissociation constant. And again, technically, this only works for 100 times K less than C. That's what we're going to do basically from here on in. So you're good to go. For the weak base on F, we're going to do something similar. 100 times Kb needs to be less than Cb, so 100 times 4.2 times 10 to the minus 4 would be 4.2 times 10 to the minus 2, and that is smaller than 0.25. So this approximation will again work. Hydroxide equals square root Kb times Cb, and if you extend that over to a pH expression, you can get pH equals 14 plus log square root Kb times Cb. So 14 plus log square root parentheses 4.2 times 10 to the minus 4 times 0.25 parentheses equals 12.01. And if you get that, you are good to go. So a lot of important information on this slide. It shows how to go from a pKa to a Ka, and that also, by the way, applies to Kbs. It shows you how to go from a Kb to a Ka, assuming they're conjugates using Kw. And then it has the 4 expressions for strong acids, strong base, weak acids, and weak bases. And if you know those, you're going to be in really good shape for the information we're going to see in this chapter. Here's a barium hydroxide solution, pH 10.66 at 25 Celsius. It says, what's the hydroxide ion concentration? And if this solution volume is 125 milliliters, how many grams have been dissolved? Okay, so let's start with the first parts. So 10.66, this is a pH. It's larger than 7. That's going to be basic. And the first thing we're going to do here is find the hydroxide ion concentration, the OH minus, and from there we can use the hydroxide ion concentration to figure out grams of barium hydroxide. Now, in the last problem, we used Kw equals hydronium times hydroxide, and we used pH to find hydronium, and then Kw divided by hydronium was hydroxide. I'm doing something different here. In this problem, I'm figuring out pOH, and pH plus pOH equals 14. And that's something we'll talk about in lecture. So if you want to find pOH, 14 minus pH, 14 minus 10.66 equals 3.34. And this is pOH. And just like we went in the last problem, we went from a pH to hydronium by going 10 raised to the power of minus pH. Here we're going 10 to the power of negative pOH to find hydroxide. So 10 to the power of negative 3.34, you're going to get this number, 4.6 times 10 to the minus 4 moles per liter. That's the concentration of the hydroxide. And again, sig figs, 2 sig figs there. So you'd have 2 sig figs there. And again, that's what the logarithm thing is all about. Now, to find the actual grams of barium hydroxide, the 4.6 times 10 to the minus 4, that's the moles of hydroxide per liter. So we'll multiply by the liters of barium hydroxide. 125 divided by 1,000 is 0.125. So the liters will cancel. This part's important. There are 2 hydroxides for every 1 barium hydroxide. So because we want grams of barium hydroxide, we need to divide by 2. This number right here is the molar mass, 171.3 grams per mole. So in the periodic table, add up a barium, 2 oxygens, and 2 hydrogens, and that's what you get. So this solution had 4.9 times 10 to the minus 3 grams of barium hydroxide. So let's say you wanted to make a 4.6 times 10 to the minus 4 moles per liter hydroxide solution from barium hydroxide. You would take 4.9 times 10 to the minus 3 grams of barium hydroxide, place it in 125 milliliters to get that concentration. And if you go back, figure pOH, etc., you should have a pH of 10.66. So these problems also illustrate a way to make these solutions. It's not just about finding the problem, you can actually make these solutions if you wanted to. Woohoo! This question basically asks what the pH is going to do, increase, decrease, or stay the same, when you add something to something that's already there. And for problems like this, all right, all you need to do is focus on what you're adding. So we don't care that there was oxalic acid already there. We're just going to look at the sodium oxalate. And the next one, we're going to look at the ammonium chloride and ignore the HCl. And the next one, we'll add the sodium, think about the sodium chloride, and the next one, we'll think about the iron 3 chloride, and we don't care really about the other things that are there. So in A, let's go back there. We're adding sodium oxalate to what was oxalic acid, all right? And we really only want to know what the pH change is going to be. So if we knew what the sodium oxalate was, like is it an acid, is it a base, is it neutral, we could figure that out. And in this problem, oxalate, C2O4 negative 2, that's a conjugate base of oxalic acid. So for this first one here, we'd say that the pH is going to increase. Oxalate is a weak base, and because we're adding a base, and bases make pH go up, we expect the pH to rise. Likewise, on the second one, we have ammonium and we have chloride. Now, if you look at the lecture notes for this section, chloride is an example of a neutral ion. It doesn't affect pH. Chloride is the conjugate base, if you will, of hydrochloric acid, a strong acid, and conjugates of strong acids and strong bases don't affect pH. So for this problem, we're going to focus on the ammonium. And like we've seen already in this problem set, ammonium is the conjugate acid of ammonia. Conjugate acid is the important word here. We're adding an acid. So this one, we expect the pH to decrease very slightly because ammonium is an acid. And then there's already hydrochloric acid, a strong acid there, but ammonium by itself should lower the pH even more than it was before. And it may be like 0.000001 pH units or something, but it should decrease the pH. The next one, sodium chloride. Chloride, we saw earlier, the conjugate of HCl doesn't affect pH. Sodium is the conjugate acid, if you will, of sodium hydroxide, a strong base. So sodium and chloride ions are both example of neutral ions, and we would expect there to be no change to the pH. So things like chloride, nitrate, bromide, those kind of things, conjugates of the strong acids, won't affect pH. And also sodium ions, potassium ions, lithium ions, conjugates of the strong bases won't affect pH either. Now, the last one, iron 3 chloride. So we already saw that chloride doesn't affect anything, but iron is what I want you to focus in on. Iron here is a transition metal, and transition metals actually do have slightly acidic properties, all the transition metals. So iron, we would expect to have an acidic effect on the solution. The pH should decrease, and as a general rule, all the transition metals will make acidic solutions when in water. As an overview too, most of the negative polyatomic ions are a little bit basic, all right, and that includes things like phosphate, carbonate, sulfate, we saw, acetate, all those kind of things are usually going to have a little bit of basic properties. Most of the transition metals are acidic. And again, the conjugates of the strong acids and strong bases, those are going to be neutral. So that's kind of a nice overview of all the different possibilities. This is a buffer question, and it says, which of the following combinations would be the best choice to buffer the pH of a solution at about 7? All right, and you're going to need a table of Ka values and stuff for this one. So remember that a buffer is a weak acid and its conjugate base, or weak base and its conjugate acid. If we look up the Ka of these different weak acids, we can relate that to the pH. And again, what I would use here is the Henderson-Hasselbalch equation. Henderson-Hasselbalch pH equals pKa plus log base over acid. And what this question is saying is that you want a pH of 7, and ideally your pKa would be close to 7 as well. Now the tables of acids and bases list them by Ka. You can turn Ka into pKa minus log Ka, or you could take pH and turn it into hydronium, and that would be 10 to the negative 7. So if you want, you could think about it from, you want a Ka, which is about 10 to the minus 7th, i.e. Ka about equal to hydronium, or pH and pKa should be about the same, both about 7. So here's the overall equation. This is again the Henderson-Hasselbalch, and when you're making a buffer, you want to start with pH and pKa as close to each other as they can, and then you can fine-tune the base and acid kind of thing. And so if you look up these values, the far right is what you'd see on the table. So Ka of H3PO4, 7.6 times 10 to the minus 3, dihydrogen phosphate, 6.2 times 10 to the minus 8th, and Ka for hydrogen phosphate, 3.6 times 10 to the minus 3. And then in this column right here, I converted them into pKa to see which one was closest. And hopefully you can see how definitely the second one, B right there, that has a pH, or a pKa, which is closest to 7. So 7.21 is closest to 7. And also the Ka, 6.2 times 10 to the minus 8th, is closest to the 1 times 10 to the minus 7 concentration for the hydronium. So definitely B is the best answer here. A would give you a buffer which was more acidic, i.e. initial buffer pH would be about 2. C would give a pH buffer which would be more basic, i.e. it would be about 12.4, so something like that. So this is the best way then to pick buffers. What mass of ammonium chloride must be added to exactly 500 milliliters of ammonia to give a solution with a pH of 9.00? So again, similar properties to the last problem we just had. We'll use the same kind of thing. And you guessed it, ammonia and ammonium are conjugates, so you bet this is going to be old Henderson-Hasselbalch again. The difference here is that we want to know the mass, grams, of ammonium chloride. And remember that ammonium chloride is the acid part, all right? So if we can find pKa, which we had on the last problem, we'll find again, pH equals pK plus log base over acid, I would solve for the moles of base, ammonia, and then you'd have an unknown moles of acid, which you can turn into ammonium. So let's see what that looks like. So like before, this is acid plus water making ammonia plus hydronium, Ka, the acid Ka, 5.6 times 10 to the minus 10. And in this problem, we're converting the pH into a hydronium, 10 to the minus 9. And you can probably see why they're doing that. Ka equals hydronium, which came from pH, times the base, which is 0.10, and you're solving for X, the acid. And if you go through all of that, you get 0.18 moles per liter, and moles per liter times the volume would give you just moles. And ammonium, it comes from ammonium chloride, so 1 to 1. This is the molar mass of ammonium chloride. So we need to add 4.8 grams of ammonium chloride to the information given in the problem to create a pH of 9. And that's a cool way to do this problem. Now, definitely, I probably honestly wouldn't do it that way. That's the classic way, and that's fine. But again, I just love this Henderson-Hasselbalch. So pH 9.00 equals pKa, which we had from the previous problem, log base over acid. And you want to solve for NWA, the moles of the weak acid. And if you do that, you're going to get moles of weak acid, 0.090, and you can turn it into grams by multiplying by 53.5, 4.8 grams. And to me, that seems a lot easier, but it is an alternative way. You can do it either way you want. This is how you can figure these kind of problems out. Here's a problem which has some personal meaning to me. I'll tell you why in a little bit. We've got a buffer, and it's got 1.360 grams potassium dihydrogen phosphate and 5.677 grams of sodium hydrogen phosphate. So let's stop right there. H2PO4 and HPO4. The Na2 pops off, you've got a -2. Potassium pops off, you've got a -1. Notice here we've got a conjugate system. H2PO4 has more hydrogen than HPO4, so that's the acid. If we look this up, then we can look up a Ka for H2PO4, and probably it's going to be some kind of a buffer problem. And sure enough, question A, what's the pH of the buffer solution? So the buffer here, H2PO4 minus, that's the acid. HPO4 minus 2 is the base, and you can see the species they come from. But the second part's really interesting. So let's say in A we make our solution, cool, and then our boss says, wait a minute, I don't want that particular pH. I want half of a pH unit less. And how can you use the same system and still get to this new pH? And I'll talk about that in a little bit. So we're focusing on A first of all. We want to find the pH of the buffer. And again, the important part is just to recognize that it is a buffer. The H2PO4 minus comes from the potassium salt. The HPO4 minus 2 comes from the sodium salt. H2PO4 minus is the acid. This is the Ka for dihydrogen phosphate ion from that table. So we're going to use this 7.21 pKa. And again, what I would do is use Henderson-Hasselbalch here. I'm going to turn both of the gram amounts into moles. So the numbers on the bottom, 141.96, those kind of things, those are the molar masses of those compounds. And you end up with these numbers right here. Then pH equals pKa plus log base over acid. You have to keep remembering which is which here. The base over acid can be moles per liter over moles per liter, but it can also be moles over moles, which is what we have right now. And if you do that, plug and chug all this stuff, your pH of this buffer, 7.81. Cool. But the next part is what's kind of interesting, because I used to work for this person, and he was a really nice guy, but he was a little spacey. So let's say that my spacey ex-boss said, okay, make a buffer at 7.81, and I did. And then he goes, 7.81? No, I meant 7.31. So pH less of half of a unit. All right, you want to decrease the pH by half. And at first it might be tempting just to trash the sample and start with brand new chemicals, and you could absolutely do that. However, if we want to make our buffer half of a pH unit smaller, that means we need to add more acid. So if we can just manipulate what we have right now and figure out how much more acid we need to use, we can still use this buffer system. We don't have to trash it. Woohoo, environmentalists. And anyway, I'm digressing here. So in the second part, what we want to do is we want to make it 7.31, not 7.81. And because the pH is decreasing, that means we need to add an acid. Acid makes the pH go down. So we're basically going to resolve that Henderson-Hasselbalch. We're going to change the 7.81 to 7.31. And remember, Henderson-Hasselbalch law, pH equals pK plus log base over acid. And we're going to solve now for moles of acid, essentially. And we'll compare that back to what we had. So if you do this, 7.31 minus 7.21 is 0.10, and that equals log base over acid. Now, we've already got the value for the base. That was from the last slide. So when you go 10 to the power of 0.1, it comes out to be 1.3, and that equals base over acid. So X here is the moles of acid we need in the new system. And when you do that, 0.032 is the answer. And if you turn 0.032 into grams, that means we need a total of 4.3 grams of acid. But we already had 1.360 grams of acid in the buffer, from you see from the original problem. So subtract that from the 4.3, 2.9 grams of acid added to the buffer will make the pH go down by 0.5. So an additional 2.9 grams of the KH2PO4 will make this start to happen. What will be the pH change when 20 milliliters of sodium hydroxide is added to 80 milliliters of a buffer containing 0.169 molar ammonium and 0.183 molar ammonium chloride? Look up values. Okay, so once again, buffer, operative word. In this buffer, we have ammonia and ammonium, and ammonium has more hydrogens than ammonia, so that's the acid. So we'll look up the Ka for ammonium. Ammonium plus water makes ammonium plus hydronium, Ka 5.6 times 10 to the minus 10th. This is what you would look up in the book. This is to find the pH before the sodium hydroxide. This will be helpful. So anyway, here's Henderson-Hasselbalch, the way I would recommend. pH equals pKa plus log base over acid. Turn Ka into pKa minus log Ka equals 9.25. And then literally just plug and chug. So you'll see here it's base over acid, 0.169 the base on top, 0.183 the moles of the acid on the bottom. 9.22 is the pH that comes out after adding sodium hydroxide. All right, and again, pretty chill. We didn't have to turn moles per liter into moles or anything like that. You just use Ka. Now, on the next part, when we figure out the pH once the sodium hydroxide's been added, remember sodium hydroxide is a base, and the pH should get bigger. Bases make pH get larger. So we would expect the answer on the second part probably to be more basic than 9.22, a bigger number than 9.22. Now, there's different ways to do this next part. The top there, I've got the pKa, I've got the Ka, and the reaction we're looking at. And when you add sodium hydroxide, the sodium hydroxide is going to attack the acid, and it's going to end up making more of the weak base. So here in this problem, first you got to figure out how many moles of strong base you've got. And here are the moles of ammonia, and here are the moles of ammonium. Now the sodium hydroxide, all right, is going to make the ammonium moles smaller, but it's going to make the ammonia moles bigger. And if you're going to do this in the classic way, you've got to deal with moles per liter. So here's the total volume. Here's the sodium hydroxide reacting with the weak acid. They'll wipe each other out, product favored, one-sided arrow, but in the process, more ammonia is made. So again, this just goes to show that the ammonia moles will increase and the ammonium moles will decrease. You can see this easier in an ice table, perhaps. Here's the moles of ammonia going down as the NaOH is added, and here's the moles of ammonia increasing as the sodium hydroxide is added to the ammonium. And again, they're increasing because you're adding a strong base to a weak acid, and the weak acid is turned into the conjugate base. So once you have these numbers, then you can use pH equals pKa plus log base over acid like we did before. Again, pKa, same number. Here's logs base over acid. And the answer here comes out to be 9.34. And if you think about it, that is more basic than the initial answer. All right, 9.22 was the answer on the previous part's problem. Now it's at 9.34. That makes sense. Sodium hydroxide has raised the pH. HCl, if we would have added that, would have lowered the pH. Acids lower pH, bases increase pH. Finally, there is an alternative version, and like we talked about in the last problem, this equation would work, I think, even easier in this than it would have doing the way we actually did it. And again, it's pH equals pK plus log, and in the top, NWB plus NSB, and in the bottom, NWA minus NSB. And again, the NWB plus NSB, that's this number right here, 0.0155, and NWA minus NSB, that's this number right here. So I like this version of the HH. You do have to use moles, but otherwise it's pretty cool. It's up to you which way you want to do these problems. Okay, so that's it for problem set number 3 of Chemistry 223, and I appreciate you being here. To assist you more with this kind of information, I do recommend that you check out the study guide and the concept guide for chapter 14. They are available both in the companion and on the website. You can also see the online-only chapter guide for this section too, which has some information that might be helpful. You might also check out the types of equilibrium constants handout. We're talking about Kas and Kbs now, different types of equilibrium. And there's also a really cool Buffers and Henderson-Hasselbalch guide, which might prove helpful. We'll do a lot with the HH equation as we go through this section. Buffers are really important, as well as types of acids and bases. Thank you for spending your time with me. I really do appreciate it, and I hope this has been helpful. Good luck with your studying, and have a wonderful day.